Hey guys, Mr. Fleming here, and I wanted to give you an introduction to the mole so you could watch this at your own leisure. You can pause it and rewind to different parts to get the ideas, but this is something that is more confusing at first, and with some practice, you'll really get used to it. But we're going to start talking about the mole, not that cute little guy. I just like those pictures. And the mole is our counting unit for microscopic particles. And this is because atoms and molecules are simply too small to keep track of individually, so we count them in groups, and these tend to be very large groups. It's like a dozen, but way, way bigger. When we talk about how many there are in a mole, this number literally boggles the mind. But one mole is 6.0221367 times 10 to the 23rd representative particles. And that's going to be 23 digits, like with the decimal point moved over. So it's insanely large. And when we talk about representative particles, it could be individual atoms or ions, electrons, molecules, formula units. We can even talk about moles of real things, but that gets really silly really fast. And we often just round it to 6.02 because we don't have time for all those other numbers. And we call that Avogadro's number. And you'll learn more about Avogadro later. A mole is, thinking about it, it's so much that it really can't be used to count anything else. There is in no way, shape, or form a mole of people on Earth. There's not a mole of pennies around. The Milky Way doesn't have a mole of stars in it. But when you have like a gallon of water, there are 210 moles of water molecules in there. So really, atoms and molecules are so fantastically small that it takes this giant number that we just can't comprehend. I'm pretty sure somebody's going to ask if there's a mole of sand on all the beaches on Earth, and I don't think the answer is yes. I think we're maybe there, but it's insane. So when we're talking about the representative particles, it will be whatever we're counting, specifically for the chemistry problem that we're doing at the time. So it might be atoms, because noble gases only group in atoms. It could be molecules of a pure substance, like molecules of water, or formula units for our ionic compounds. So anytime you see just one of these dots, we can represent it as either a single particle or a mole of particles, which we'll do for all of our balanced chemical equations. With the formula unit, it's the two dots that keep repeating over and over again. So it doesn't really matter if it's a pure substance. We'll get that information to you. And all you need to know is that if you have a mole of something, you have a whole lot of it. So mole of sugar, 6.02 times 10 to the 23rd molecules. Mole of helium, 6.02 times 10 to the 23rd atoms. Now, if we're ever asking you to count 1 mole of something, you just multiply. So 5 moles of sodium would be 6.02 times 10 to the 23rd times 5 moles of sodium. There's 3.45, you just do the math on it and use a calculator. Don't make yourself crazy with it. Now, why this number? And this is kind of a weird number to come across. And what somebody did, what Avogadro did when he was counting individual particles, was try to standardize it. So a mole is actually what it takes, a mole of carbon atoms, so carbon was used as the standard, weighs 12 grams. And if you remember the periodic table, carbon is, it's got 12 for its atomic mass units. So a mole is the number that converts atomic mass units into grams. You need a mole of something to make its gram weight AMUs. This is going to come up a lot later on. So when we are measuring stuff out, like I don't count an individual mole of particles in the lab. I'm going to weigh out something, and then we're going to have to do a conversion to relate the amount of moles to the mass as we're doing it. And luckily, the conversions are all on the periodic table, so you don't have to memorize or look up anything. It'll just be there. So when we have our atomic mass number, that number at the bottom there for carbon, that's the relative atomic mass of an atom of an element, and it's also the molar mass of an entire mole of those atoms. So an entire mole of carbon is this 12.01. The measurements weren't exact in the beginning. So when we are converting grams per mole, we just get out our periodic table and you can look and see, oh, what does zinc weigh? And you can ratio it out. So you can get your answers that way. And oftentimes you're going to get much smaller numbers of moles because it's a whole lot of particles to count to get kind of a reasonable amount of grams in there. So we will get way more practice than you will ever want on some of these concepts, but we are going to be converting grams of specific substances into atoms and moles so that we can have them relate to each other. And I'm going to stop this now before I make you guys do any work on this quick explainer.